want to thank everybody for joining today to RV.NET User Group's main meeting. This is traditionally a physical form meetup that we have regularly, first Thursday of every month. But in these COVID times, we've reverted to having it virtual only. Hopefully here soon, in maybe a few months, maybe going back to a physical form. Not sure exactly the timing, but one day we expect to get back to our physical form. But until then, we enjoy having the virtual meetups here and having your presence virtually. I think it's worked out so far for us really well. We've been able to get some really great presenters and really good videos that are also available on YouTube afterwards. So check those out. We've had some really good collections so far. This month is no exception. We've got a great presentation lined up for you. Akka.NET and presented by Shawn Whitesell, originally from Philadelphia area. Shawn has 15+ years of experience solving problems with an IT professional developer for commercial, nonprofit, and federal clients. He's currently a technical director at CapTech Consulting. He highly recommends you check them out. Aside from loving his work way too much, there's a good chance he's enjoying being a new dad, sipping great beer, exploring the Arlington area, or singing somewhere. You can find him on Twitter at sjkillian or blogging not nearly enough at ShawnKillian.com. He doesn't bite. Reach out and say hi. All right, Shawn, take it away.
Great, excellent. Well, thank you for having me out. I know that in these virtual times, it's something where you've been able to get some great speakers, so I'm happy to break that streak for you this evening. The really nice thing about this, seriously though, is getting to participate in these user groups that otherwise might be quite a hike for me to participate in. I think that user groups are phenomenal, and I think it's a really important way for everybody to stay connected, discuss new technologies, just kind of be together as a community of developers. So I'm really happy that this user group exists, and I'm really happy to be here. So thanks for having me. So today we're going to talk a little bit about Akka.NET and the actor model. And so I've got the URL for the slide up here, and just so you know, I've got a demo later in this talk that I'm doing for the first time. So just to show there's no tricks up my sleeve, I have a Terraform file here. I'm going to go deploy. Oops, no, I'm not. I'm going to go deploy a virtual machine for the first time to the cloud real quick. So we can start off with an empty virtual machine. So that's going to run in the background while I do my talk. But I just wanted to be clear, no tricks up my sleeve. I'm creating everything from scratch right now in the background, and we'll do some stuff a little later with that infrastructure that's being created. So okay, back to the presentation. So what we are going to cover today. We're going to talk a little bit about why the actor model and reactive programming matters. We'll talk about the Reactive Manifesto and the attributes of the Reactive Manifesto. We'll give a little bit of a history and an overview of how Akka.NET came to be. I've got secondhand knowledge, right? I wasn't there, but hearing some things from some of the folks and the creators, I can give at least a high-level overview of how it came about. We'll talk about the concepts of the actor model and the benefits, and then we will of course save enough time for some demos at the end to sort of introduce conceptually how the actor model works. So before I start off my talks, I always like to give acknowledgements where they are due. And the first one of these goes out to Roger Johansson. You have his contact information up there on the screen. So Roger is one of the creators of Akka.NET. He actually also is the creator of the proto-actor framework, which I think he views as a sort of successor or complementary framework to Akka.NET, which allows you to do some lightweight actor model things across C# and Go. So really interesting model, or a really interesting project there to check out as well, the proto-actor project. One thing I like to point out about Roger is that if you see a graphic in this presentation that looks decent, doesn't look like it was made by a child, that is Roger's handiwork. He's allowed me to use some of his great diagrams in this presentation, and so I make sure to thank him up front. So if you see anything that looks polished like a graphic, that is Roger's, and we thank him for that because I think it explains things very well. I also like to put up this tweet from Roger because I think that it helps us understand a little bit about how some of us can find ourselves feeling like a beginner or a fish out of water. Roger is someone who is incredibly accomplished as a developer, and I also love that even he has trouble occasionally with Azure functions. And so I like to put that up there for the folks out there who feel like sometimes they're thrust back into the land of beginners, especially because the actor model is a bit of a paradigm shift for developers. And so it's important, I think, to think about getting out of our heads in terms of classic object-oriented thinking and stretching our minds a little bit. When we do that, we can feel like beginners. So just remember, people like Roger feel that way as well. I also like to thank Pettbridge for this. Pettbridge is the company that sort of is a caretaker of the Akka.NET project. They offer commercial services on top of that. Aaron Stannard, one of the founders of the Akka.NET project, is actually the CEO of Pettbridge, the owner of Pettbridge. And so they do phenomenal work in the commercial space, helping clients implement the actor model, reactive programming, the Akka.NET. They also have a fantastic bootcamp series, which is one of the things I like to point out. So if you're interested beyond the presentation today, the idea of the actor model has you interested, a great next step is to go to Pettbridge and sign up for their bootcamp. They kind of give you like a drip email, and it works really nice as a way to get you introduced to the concepts and kind of build on your knowledge at a reasonable pace. So I recommend doing that. I'd be remiss if I didn't at least give a little bit of a shout out to the .NET Foundation. I assume and hope that the folks in this group are probably aware of the .NET Foundation, at least at a high level. I really recommend, if possible, you look into the foundation and look to get involved with it. The .NET Foundation really seeks to support open source efforts in the .NET community, and they work really to help library authors, to help the community. They're trying to do better all the time. And the best way for them to do better is for people like us in these user groups to join them and help out. They've got working groups. They've got a bunch of places where folks who are interested can jump in and make a big impact across the entire community. So if you're interested, if you have not already joined the .NET Foundation, I recommend that you do so. There's a form online that you can fill out. And I think it's a really phenomenal organization that's worth your time looking into if you haven't already. So, and last but probably least, I'm Shawn. I'm Shawn Colleen. Happy to be here with you. I've got my contact information here, but I'll send the links to you afterwards, and it'll be on the screen throughout the presentation, so we can skip over that part. So let's talk a little bit about why this matters. Why do we care about the reactive model? Why do we care about the actor model? So, previously, or even really today in a lot of cases, the web applications that we build are often based on request response. Right? So something makes a request, something returns a response. But this is hard to manage in terms of state and in terms of the kind of real-time demands that customers care about. Really what happened that spawned the reactive manifesto and reactive programming in general is the idea that we really need to keep up with our users' demands. Our users want real-time. Our users want quick feedback. Our users want applications that don't fall over when they're deployed or when the load hits them. And so out of this comes the idea for a sort of different paradigm of thinking about programming than the traditional request response model and the traditional object-oriented programming model. So in comes the reactive manifesto. The URL is here, but the idea there is that we need, as developers, to evolve with our users' expectations. And certainly, I think that I've written enough request response applications to understand sort of where the pressure points are, and many of you may have as well. And the reactive manifesto sort of helps us, or aims to help us, think about development in a way that will evolve to our users' expectations. So what is a reactive system? Great, there's a manifesto. Everyone's got a manifesto. That's great. So the reactive, but what are reactive systems? So reactive systems are responsive. This means, and this is by definition, in order to be a reactive system, a system must be responsive. You have to return answers to your queries and requests very quickly in order to meet your users' needs. You must be resilient, and by that we mean the ability to recover when something goes wrong, or when things happen that are out of bounds for our application, has the ability to recover and keep fulfilling users' requests and needs. Reactive systems are typically elastic. They can scale up and scale out with ease, and a key component of reactive systems are that they are message driven. The basis of the application is formed around components passing messages to and from each other. And so as a result, reactive applications tend to be pretty flexible in terms of how they can be built and how they can be refactored and how they can be extended. They are loosely coupled because we are thinking about actors in sort of isolation, or trees of actors in isolation. They tend to be very scalable because, as I mentioned, scaling up and scaling out are key characteristics of a reactive system. And that makes them a little bit more flexible, a little easier to change. And the key thing for me, I think, is that they're fault tolerant. There are many we'll talk about this in a little bit. There are many places along the way for the actors and the actor model to recover. So should something go wrong, should something need some additional support in order to process something, the reactive system is a very powerful way to achieve that objective. And I mentioned this before, but of course, they have to be responsive. Reactive systems tend to be pretty darn fast. And we do that by enabling a certain way of thinking and sort of changing some of the constraints of our prior thinking about the request response model. So overview of the actor model in general. So the first thing I want to stress is that actors as a concept are not a new thing. They're newer to .NET. They've been around in Java for a little while longer, but even going back a little farther, I know this is not an interactive forum, but this is typically where I would ask who thinks that who thinks they can name sort of when the actor model and the actor model based thinking came about. So we don't have to go off mute and do a bunch of those answers. I'll throw it out there. So Carl Hewitt released his white paper on this theory in 1973. So the actor model has been around. It's not a new thing. It's sort of a new paradigm for those of us who've done traditional OOP for a while, but it is not a new concept. It's been proven out for quite a while. And actors are actually used in quite a few places, and the actor model is used. So some examples there are, for those of you who've worked with Erlang. Erlang is heavily based on the actor model, or uses a lot of concepts from the actor model, particularly the fault tolerance structures of the actor model, which we'll talk about in a little bit. The actor model has been used at Box, at LinkedIn. If you've heard of Microsoft Orleans, That's another library for that embraces the actor model. And so games like Halo and other platforms that use the actor model as well. WhatsApp uses the actor model, and you'll also traditionally tend to find it in those sort of battle-tested fields where applications absolutely cannot fail. So telecommunications, finance, data crunching, event streams, even in a lot of neural networks, they're sort of trained and behave as sort of actors that pass messages to each other in a lot of instances. And so that's a little bit more of a loose association, but oftentimes they're used in those ways as well. So actors are definitely all around us. So what about Akka? What is Akka? What is Akka.NET? How did that come about? And so the way, and again, I'm going to poorly paraphrase this, so I really hope Aaron doesn't watch this because it's going to be a terrible retelling of a story that I heard him tell. But in general, the idea was that Aaron had founded a company called Markup Analytics, and their goal was to sort of fire off events when a user did maybe a set of 3 different actions. It would show them a promo code, right? Or those kind of analytics. So the key was to gather key insights from what users were doing and use that to adapt and take those analytics and respond to those users. So they had built that out using, I think it was SQL Server and a traditional sort of web app API kind of web model. But what I think he described it as quickly falling over in a pile of fire when it started to get any kind of traffic, because of the way you couldn't depend on the order that messages were coming in. So you had to kind of allow for message 4 to come in before message 1, or not arrive at all because of the nature of the transport protocol and HTTP, and some things that maybe would go or would not go. And how do you acknowledge if those messages were received? And so he had sort of a conundrum on his hands. And he said, the way he described it, I think, is he said, I finally figured out what to Google for. And he said, I had a sort of a stateful reactive systems problem. And once he started Googling that, he stumbled on the Akka project, which for a long time at that point, or at least for some years, lived in the Java ecosystem, was a robust production-ready library. And so he had sort of 2 choices. He said, well, I could rewrite my whole product in Java, or I could rewrite this piece of the product in .NET. And this library in .NET. And so he talked to and around this time he sort of met up with Roger. I think they kind of around a shared problem there. And they talked to the folks at the Akka project and gave them allowed them to use the name Akka, and so thus Akka.NET was born. So they're separate projects, but they share a lot of the key concepts, Akka.NET having been adapted for sort of use in .NET world and in our .NET universe. And so that's sort of the origin story of how Akka.NET came to be. And actually, since that time, even though Aaron's company Markup Analytics didn't quite go where he wanted it to, he actually found that a lot of people out there needed an understanding of this kind of system and really needed the abilities, the capabilities of this library in their own companies. And so thus Pettbridge was born, and he's been doing great work with them ever since, helping companies all over implement this sort of paradigm. So we talked about actors, we talked about Akka.NET, great, like what are the concepts? What do we mean when we say the actor model? How is it different than what we've been doing? So the first concept in the actor model to think about is that everything is an actor. So and by what I mean by that is that a lot of times in object-oriented programming, we hear, okay, everything is an object, right? So in the actor model, everything is sort of like an object with superpowers. So you inherit everything that you're doing from the concept of an actor, and that provides certain functionality out of the box. So actors are sort of a container for state and behavior. Every actor has a mailbox. Every actor can have children or child actors. Every actor can be supervised or have a supervision strategy that governs it. And so this is an important concept, and we'll flesh this out a little bit more when we talk about fault tolerance. But the first basic concept there is that, well, not really basic because it's difficult to wrap your head around at first, but the idea is that in this kind of framework, everything is an actor that is part of an actor system. You won't really be working with objects that don't inherit from the concept of an actor in most cases, because we want the benefits that the framework provides us, and so we sort of stay in those constraints, and everything within our system now functions as this thing called an actor. So as I mentioned, that actors are sort of an encapsulation for all of that state and behavior. So it functions as one sort of unit of responsibility. And messages can come into it, it can adapt and change its state and perform other behaviors based on the messages that actor receives. And so there's also the idea of every actor has this actor reference, which is a way to locate that actor within an actor system. So that sort of reference encapsulates all of that behavior and responsibility. We'll take a look at that in a little bit. So another key concept there is immutable messages. For those of you who aren't familiar with the idea of immutability, just the 2-second explanation, right, is it creates messages are objects that you should not change their contents after they are created. And so we take some steps here to ensure that is the case, because we're passing these messages around, and part of what the system depends on is that message is the same when it arrives as it was when it left the other place. So we're changing contents and memory sort of mid-flight on these messages. It can cause some undesirable behavior. So every message that an actor sends is immutable. It is designed to not have its state or contents changed. Actors by reference is the next very important concept of the actor model. So when you think about actors by reference, we don't actually, Whereas an object, we might get a reference to an object in a variable and act upon that. With an actor, we only ever talk to something called an I-actor-ref interface. And this enables a concept called location transparency, which we'll talk about when we get to the benefits. But a key concept there is that you're never really working with an actor that's a direct reference to an object. You're always working with this idea of an actor reference. So you don't know where that object is. That has many benefits that we'll talk about, and we have some demos to show about that in a little bit. The other key component or concept of the actor model is something called props. These are things that you pass to an actor so that it can be instantiated, or sort of a recipe, in other words, for creating an actor. And I thought this was like short for properties for a while, and I wasn't quite sure, but it's really kind of like an actor joke. Like, actors need props to do their job, so you pass props to an actor so they can perform. Cool programmer humor. But so I thought that was a little bit amusing. So just to review then, every actor has an address where it exists in the actor system. We'll look at some examples of that in a second. Every actor lives within a context. It's somewhere within an actor system, which is a hierarchy of actors. And so no actor is just sort of off on its own in some other system somewhere. It's all a part of a hierarchy or a tree. And so they have a context. They may have children, they may have parents, but they all have some kind of context that they live within this actor system. Every actor has supervision, whether by the framework or by a strategy that you choose and provide, that it implements at runtime. And every actor has a mailbox where they can receive messages in response to which they can change their behavior, they can send other messages, they can change their own internal state. And lastly, every actor has a life cycle. There's sort of a standard life cycle where you can hook into events around restarting an actor or starting or stopping an actor, so that you can kind of get some of the flexibility there as your actors are created and destroyed. So actors have an address, and so the format of an actor's address within an actor system is typically as follows. So first we have the format or the network transport. So Akka supports TCP out of the box. It's configurable with others. You can also even bring your own network level implementation should you desire. It's a package that can be imported, and you can write your own custom code. But typically the address begins with the transport protocol. Next up is the name of the system itself. Now here I'm calling it my system. Now this is key because actors can only talk to other actors that are in the same system by default, or you have to explicitly say what actor system they're a part of. Typically this is to make sure that if you've got clustering in place, or if you've got actors that live in different systems or different areas, that they will not cross communicate when they shouldn't, and two, that you kind of have an understanding that this lives in an entirely separate system, an entirely separate hierarchy, and the appropriate kind of boundaries and considerations for design should apply there. So you supply the name of the system. Next is the server path or the machine location where that actor is located. Now, as I mentioned, this is what the system understands to be the actor's address. You typically will not refer to an actor by this full path. This is just that every actor under control by the framework has an address. So it does live somewhere on a machine. It's the framework that understands that, though. And so in this case, the actor is running at localhost on port 8080. And lastly is the idea of the actor hierarchy. So everything within Akka.NET lives in one of two hierarchies. There's the system hierarchy, which is where the Akka framework has all of its actors, its system level actors. And then there's the user level hierarchy. Anything that we do within the framework falls under that user level hierarchy. So we'll show a graphic of this in a little bit. So in this case, we have an actor called Hello World Actor, and it exists under the user hierarchy. So it's sort of a top level actor called Hello World Actor. So every actor has this kind of a path associated with it. I mentioned the life cycle, and so actors have the ability to sort of replace or restart, right, or be destroyed and recreated. So let's take an example of when an actor is restarted, for example. So when an actor is going to be restarted here, we have first off pre-restart is called on the old actor instance. And so at this point you can do certain things. Maybe you want to stash all of the messages that were remaining for that actor. Maybe you want to let other actors know that this thing's about to be restarted or shut down. So pre-restart is called, and then restart is fired there. And then a new instance is created here. A new instance of the actor. It then replaces the old instance at the same address, and then post restart is called on the new instance. So hey, we're restarted now, so maybe at this point you want to gather those messages that you had saved before the last restart, and you want to kind of put those in the mailbox. And Akka has some things to help you with this that we'll look at. And then once that post restart method is called and things are restarted, then it can resume the functionality, and then you have sort of the actor instance that has been replaced at that point. So that's the example of as actors are shutting down or are restarting, you have the opportunity to hook into those lifecycle events and make the appropriate adjustments in your system or do the appropriate things to respond to those happenings. So I mentioned context and actors living in a certain hierarchy. So the key here is that we use, rather than saying like, hey, new actor, or var x equals new actor, instead we always use something we use context.actor of. And so we may create an actor system, right? That's the sort of heavyweight thing. You typically only have one of them per application. And then you will say actor system.actor of, and that will place an actor into that system's hierarchy. Similarly, if you have a parent actor and you want to create a child actor, it'd be sort of a, parent.actor of would create a new child actor. And that's to ensure and sort of enforce that those actors live within a context. And so it's pretty subtle that every, context isn't always available depending on what kind of actor you're inheriting from, but for most operations it will be, and every actor does have the idea of a context. So for example, just to give you an understanding of why we work with actor refs. So this is my favorite graphic probably of Rogers. And so we have the idea of we're sending messages to an actor ref here. That then goes over some transport that we don't necessarily even need to know about or care about. It arrives in the actor's mailbox. Messages are arrived and they are processed in the order in which they arrive, which is a key concept for the actor model. Messages are going to be processed in the order in which they come into the mailbox. As each one of those messages are processed, the actor might change its behavior for the next message, or it might adapt its own internal state, or it might do something with supervision. Maybe something has gone wrong and it needs to do something with one of its child actors, or it fails and needs to blow up, or maybe it sends a message to its child actors, or it fans out to them, or it sends some small piece of processing to one of its child actors. So those are the kind of things that can happen when a message is received by the actor. That all comes from us interacting with this concept of an actor ref. So the nice thing is that's sort of transport agnostic, where we're not sure, we don't have to know right off the bat where these other actors are living. Another important thing to note, for those of you who see this kind of queuing, you may say, ooh, that looks like polling. That seems like it might be pretty costly. This is an event-driven thread, so there's no polling being done here. Actors are only doing work when they are processing an incoming message. So other than that, they're incredibly resource efficient, and you're not doing that kind of polling that you might be concerned about in other systems where you're dealing with queues or things like that. So let's think about when things go wrong. So there are faults when you have a fault in the classic, maybe an old school, I'll call it old school at this point, or legacy .NET system. So, just to give an example, maybe you've got a service, it has some idea of a business logic layer. Maybe that connects to some sort of data access object, right? This is taking you back a little ways, probably. Maybe that data access object is using EF or something along those lines, and then there's an entity. So what happens when something goes wrong at that level, right? You have to have the appropriate exception handling all the way up the chain. And more often than not, what happens there is that results in a failed requests, right? So exceptions, if you're not doing them perfectly, and I know I'm not doing them perfectly 100% of the time, chances are you're going to miss something, right? Or you're not going to implement the exception flow, or it's going to be really performance or costly sort of exception flow, or things are going to just bubble up to the top. We're going to say, oh, that request failed. And then who sees the failure of that request? It's going to be your end user, or some kind of handling that you're going to have to do where the user has a suboptimal experience. So it's also not necessarily clear who's responsible for handling these errors. Like, should that all be done at the service level? Should we really try to catch things at each level along the way? Do we need to kind of agree on a pattern across our team for that? How does that actually work, and what are the rules behind it? It's not always consistent. In fact, I would argue it's rarely consistent in enterprise applications, at least. So how does Akka and Akka.NET handle this idea? So similar to Erlang, there's this idea of the error kernel pattern. So as I mentioned, every actor within Akka.NET lives under this top level hierarchy. There's the user hierarchy and the system hierarchy. Anything we do is in this user actor hierarchy. So there's the user actor, the parent actor, in this case /user, is responsible for all the children below it, aka everything we create. And every child actor we create of an actor, the parent is responsible for the child. So this might seem a little strange, like, okay, we have to think about how these parent actors are responsible for these child actors. But one of the nice things about that is that we're actually thinking about it upfront at development time, rather than, oh no, something went wrong. How do we maybe catch this and handle it at runtime? When we think about these hierarchies, and we'll show some examples of how we might think about these hierarchies, when we think about them this way, it forces us to sort of be conscious about our handling and our supervision strategies upfront, which forces us to be conscious about what kind of work we're doing and what kind of faults we might experience. So Akka.NET has different strategies for how to handle fault tolerance. I show two examples here. The first one is the one-for-one supervisor. So in this example, say we have an actor, we've called it A1 here, and we have an actor underneath that called actor B1. It's a child of A1. And then B1 has two child actors, child 1 and child 2. What happens when, the strategy here for the actor model is that we always want to push dangerous work lower and lower and lower in the hierarchy. And that's because when a failure happens, we have built-in chances to recover at every level in that hierarchy, where we can restart an actor and reprocess a message, or we can stop the actor and say this actor should not receive any more messages, or we can just ignore the error and carry on and process the next message. So there are different strategies here. In this case, the C1 child here is blown up and experienced a problem. So what happens is it goes back up to the parent and says, how do you want to handle this? The parent is using a one-for-one supervisor model. There are many built-in out-of-the-box supervisor models that Akka.NET allows you to use. So this is one example of those. And then from there, it can actually restart that one actor or do whatever needs to be done with that one actor. Similarly, the all-for-one supervisor here, what happens when actor C1 or C3 in this case blows up, maybe it bubbles up to the parent here, B3, and says, what do you want to do? And it says, well, this is in an inconsistent state, so I want to restart or stop or do something with all of my child actors. I don't want to just restart the one, I want to do something where I restart or I stop all of my child actors from doing things. And so, of course, there are many, you have if statements, you can do supervisor strategies that only matter if a certain error is thrown. You have a lot of ability to customize that in your development and design. So the idea here is that these out-of-the-box supervisory structures come with an actor model framework like Akka.NET. So what are the benefits of Akka.NET? So great, we can do exceptions now, we can do error handling now, we can do request and response now. Like what are the benefits? One of my favorite benefits of the actor model is that it is async by default without me having to think about asynchronicity. And what I mean by that is, again, I don't know about this audience, but I'm not writing perfect async code every single time. And if I had $1 for every time I heard about a dev getting bit by some edge case bug around async, I would be quite a wealthy person. But the issue here is that, or the benefit here is that with Akka.NET, you're not thinking about writing or awaiting different actions. You are sending a message to an actor, or your actor is processing a message. And in the space of processing that one message, because we are making guarantees that messages are coming in the order in which they are received, they're only coming in one at a time. So you only need to think about what you're going to do when you receive one of a given message. So you don't have to create a different asynchronous data structures to handle your tolerance and thread safety there. You can actually sort of operate on things. You don't have to create an immutable list, or you don't have to create bags of things, a concurrent bag of things that you can store things. You actually can process these things one at a time, which I find greatly simplifies thinking about asynchronicity, at least for me as a developer. So another one, recoverability, we talked about that a bunch. If something goes wrong, you have a chance at each level of that hierarchy to recover. And you've thought about each of those chances at development time. And so the result is that oftentimes, if something happens lower in the hierarchy, there's a very good chance that you'll be able to recover, retry, do something with that actor that will allow you to have the appropriate response that won't impact your user base and their overall experience with your application. And that's huge, especially if you're in critical kind of systems that really are those sort of can't fail kind of systems. The ability to have that recoverability is crucial. So child actors, some of the ways that folks refer to them as character actors. So maybe you have a child actor that does some work. Other times you might have a character actor that just shows up, performs a small part, and then you kill it off. And that's completely reasonable in the realm of actor-based design. The other nice thing about that recoverability is you can scale out small pieces of work across many actors. And if one of them fails, one small piece fails, that piece can be retried. All of the other actors are unimpeded in the progress they're making towards that work. So we keep pushing that work down and down and down into those child actor layers, which enhances our ability to recover. The benefits of actors and the actor models also that they're cheap. Sorry, actors, it's a terrible joke about how actors are cheap. But in the case of Akka.NET, like I mentioned before, actors aren't really using any CPU unless a message is actually processing. And I checked the Akka.NET website just to get the stats on this. And their website claims, at least so far now, that you can fit roughly 2.5 million actors into a gigabyte of RAM. And that on a single machine, at least, of course, the throughput goes down when you introduce a network, but on a single machine, at least, there are millions of messages. In fact, I think close to 50 million messages per second can be processed on a single machine. And so that is quite the numbers. And even if the real world numbers are a little less than that, the key there is that you can do a lot with the actor model. So when you think about actor structures or what that hierarchy of actors might look like, it might be possible to have an actor per entity, or an actor per aggregate type of entity in your system, that you can then think about how you want to interact with that or process that or do things when messages arrive to those actors. So it enables some of these great like fan out kind of architectures where you can really have a lot of these actors spun up without worrying about how much resources it's going to really be crushing your infrastructure with. That location transparency that I mentioned earlier is key. So think of like using actors by reference is like using a cell phone grid. Right, so I don't have to know where my brother lives in Philadelphia or where my brother is currently. I think he's in Philadelphia right now, but I can call his cell phone number, right? I have that reference, and the network, that framework for our phone call is going to route my message to him, and he'll be able to receive that. So same thing with actors. I have an actor reference that points to somewhere. And the nice thing about that is what that means is that at runtime or by configuration, I can change where those actors live. So, at runtime or really just before runtime as part of a configuration file, I can say, hey, I know you're referencing one actor there, but instead of referencing one actor, let's put 5 and put them behind a router. And I, the caller, don't know any different from that. I just know that I have a reference that I can send a message to. And that's sort of some of the beauty of Akka that allows us, and Akka.NET that allows us to scale up and scale out. So that can be done on the same process or different process, same machine or different machines entirely. And we'll show examples of all of that. That's one of the reasons why my little infrastructure piece was spun up at the start of this talk. Akka is also great for the idea of state machines. So as you process a message, I mentioned that an actor can change its behavior for the next incoming message. This allows you to think about the idea of state machines or what the state of a current actor is. If I have a green light and then I say, okay, I've received a message that says now the light is red, and I change it to a red light, and then traffic can't go at that point, right? You have the idea of this state machine. There's actually a great library, I think, or component, I maybe misspeaking a little bit there, specifically for state machines within Akka, if that's the kind of thing you have a really world-class need for. There's a package available specifically for that. That concept is called become or unbecome. So an actor can sort of become a different version of itself or unbecome that version of itself and go back to its default behavior. And that will change how it processes the next message. So I mentioned configurability. And one of the keys there is this idea of Hokan notation. Hokan, right? We've heard of JSON and YAML. Hokan is a sort of a different take on that, called human optimized configuration object notation. Say that 5 times fast. So it allows that sort of layered configuration and fallback that you might expect with other types of configuration. We'll show some examples of a Hokan configuration in this talk. But the key there is that Hokan configuration actually allows you to change things about the actor hierarchy and how and where actors are deployed without having to modify the code that you've written to interact with the actors. So when we think about scaling, right? So, okay, back in the old school days, right, we had single core CPUs, right? And so no matter what you were going to write or how much processing you were going to do, right, no matter how many cores you had, it didn't matter because our code was written for single cores, right? Things were single threaded. And so we really didn't have the ability to break out or utilize more than that functionality, right? So of course, then we went to multi-threading, right? So we go to multi-core processors. And so then maybe at that point you would adapt and use use TPL or use async await. But so what happens when it's not enough? Right? Typically in this situation, right, we built an application and we say, okay, we've got a machine now with 32 cores, we're paying a bunch for this hardware. It's just not enough to sustain what we needed to do. Well, what happens? And usually at that point, some bad things happen from a business perspective. You think, oh, shoot, well, now we have to introduce more than one machine. And as soon as we get to that point, we have to think about the kind of infrastructure we're going to put between those machines, right? Are we going to introduce queues? Are we going to introduce an event grid of some kind? Are we going to introduce a service bus? How are we going to handle this machine-to-machine communication? Because we need these systems, these actors, to be able to talk to each other. So when it's not enough, usually what happens is you hit some kind of major walls there, and you have some infrastructure rewrites or you have some architecture changes. And if you're lucky, you can kind of detect those, right, and get ahead of them and build it out. Or these days, if we know something's going to scale, we have some pretty standard patterns to deal with that stuff. But scaling up and scaling out were previously different conditions. So with the actor model, the key thing to think about is that adding more machines or adding additional hardware to your problem across machine boundaries actually doesn't introduce or doesn't need to introduce that much more complexity into your code base. And we'll show an example of that in this talk. So that's the key benefit there. One of the key benefits of the actor model is that scaling up and scaling out become almost the same thing. There's very little distinction between the two in terms of the design considerations that you might make. And that might feel a little wibbly wobbly. So let's get to the favorite part, and let's see if I crash and burn on some of these demos as we go ahead and talk about that. So while I pull that up, I need to do one more piece of my infrastructure that can run in the background there. So while we do that, let's take a pause. I've just thrown a lot of information at you, and let's see if anybody's got any questions. And so if you do have a question, feel free to unmute, and we'll go from there.
Yeah, I've got a question.
Great.
Do the messages contain state information?
Could you extrapolate a little bit what you mean when you say state information?
Yeah, let's say you have a transaction that has to take 2 or 3 interactions. Can you pass the state of the first interaction between, I guess, actors?
So typically what you would do is you would sort of model that in an aggregate fashion somehow. So you would have an actor that can receive messages about things that have happened perhaps, and that actor will have an internal state that it can then modify. And so let's say you have an example where an actor might need to say, okay, when these three things have happened, I'm going to fire off a message to this other actor. So as message 1 comes in, it says, okay, item A happened. Then it reads the next mailbox and it says item B happened. Right? I don't care about that one, forget it. Next message, item C happened. Okay, now I'll check that box in my internal state. And then the next message it gets, it says, oh, item B happened. Oh, I'm going to check my internal state. Oh, I've got those 3 things that are needed. Now I'm going to send off that message. So you sort of encapsulate that state or that idea of state in an actor. You typically wouldn't pass around state information from message to message. Does that answer your question?
Yeah, it does. Thank you.
Okay, great.
I asked this in the chat, but I'm struggling to understand like how this would work. Like what kind of real world scenarios you would use this for, and in particular, like a parent-child actor relationship. When would you do that? Or
sure. So I'll give you an example of a small app that I built previously for going through open source contributions that you've made. And so it used OptoKit.net. And the goal was, based on all the forks that I have in my GitHub account, go out to all of those projects, go through every pull request that's ever been made against those projects and bring them back to me. So the way that I did that, right, is I had the idea of, I had a projects, a user hierarchy with myself. I had projects underneath that. Every time I created a project hierarchy, it would send a message to a GitHub crawler actor that I had elsewhere on the hierarchy to go and see if some pull requests were found. If pull requests were found, it would send a message to that parent actor, which would create a child actor to represent that pull request. Now, in that case, that was more informational. Those actors for the pull request weren't really doing anything at that point. But the GitHub crawler actor, what we had done is we allowed various people to give me an access key to utilize their GitHub credentials. So that GitHub actor fanned out across several actual actors, each one that was associated with a key that allowed it to sort of do this crawling around robin style. And each of those child actors, what would happen is when GitHub hit its timeout, that actor would actually stop, would send its messages over to the other actors to continue processing. And then once it was able to resume again, it sent a message saying that it could resume again, and then it would start receiving those crawling requests. So that was a way that we could respect GitHub's timeout functionality and kind of keep that state and keep track of that without really having to do too much additional work. It was really just an additional message that the actor received and using some of the framework's capabilities out of the box. And that allowed us to sort of do this real-time processing that scaled pretty large. Honestly, I really only had a personal use case for it at that time, but it did quite a lot of work in a small amount of time using that OptoKit library, and I was able to keep all of those actors compartmentalized. So that's one small example. I know it may not address your question universally, but does that give some idea of what I'm thinking there?
That helps immensely. Thank you.
Oh, great. So what I just did here, you may have noticed, I stopped sharing my screen, but I pulled up my VS Code instance to look at my infrastructure, and in true Shawn fashion, I forgot to type yes for Terraform, so it had not created that infrastructure. So I just typed yes, and it is now created. So don't mind me for a moment. I'm actually going to share my screen just to show you what I'm doing. I wanted to demo this, and sorry, go back to Zoom so I can share that screen here. This is I'm just
me a lot, by the way. I always forget to press yes.
every time.
Yeah.
So we've got here our assuming you can see my Azure Dev portal here, I've created a resource group with my Terraform command called Akka Intro Resources. That gives us a public IP address that goes to an Ubuntu VM, a Linux VM that I have created. And so what I'm actually going to do here is I've got handy dandy WSL here in my window. And what I'm going to do is I'm going to SSH into that VM here, as I've got that here. So I'm going to go ahead and SSH into that. Now, of course, I've got, this is for demo. I'm destroying it afterwards. So don't try to attack it during, but it'll be destroyed not long afterwards. I should use the SSH command correctly. And the reason I'm doing that is because I'm actually going to, see if that was correct. Of course, I had demo fingers. Let's try that one more time. I have it in the variables because, again, it doesn't quite matter here. So what we're going to do in this case is we're actually going to pull my repository that I'm going to use on my Windows machine, and we're going to use that to do some things here. Okay, let's try this one more time. Nothing like live copying from your variables. So we'll use the super secure the password at 123 exclamation point. Okay, great. That's always fun. If I don't do that, then we'll just return to it in a second. That's okay. I will get it right one of these times. There we go. Okay, so please hold your applause. But I will go ahead and clone that repository. And the reason I'm doing that is that I'm going to show you that we're going to be using the exact same thing. I have no tricks up my sleeve. We're going to be using the same presentation repository that I'll show you in just a moment. I think that's all I'll run this install stuff here to get .NET 5 up and running on this machine, and that should be done in a second. Okay, so while we're doing that, I'm going to go ahead and switch screens here to my demo component here. All right, and we should hopefully see a Visual Studio window. So if you're not seeing a Visual Studio window, definitely let me know. So in this case, what I want to do first is we're going to run a quick example of a hello world style application that uses the actor system. So Akka.NET works on .NET 4.8. In this case, we're going to use .NET 5 for these examples because I like it better and I like working with it, and it's a joy whenever I get to do so. So we're just going to use .NET 5 in this case because I enjoy it. And for those of you who aren't familiar with that terminology, .NET 5 is the way forward for Microsoft, and .NET is a continuation of .NET Core 3.1. So .NET Core is now the way to go. So if you are still on legacy .NET Framework applications, as many of us are, so many of my clients included, one of the things you're going to want to do is think about a strategy for upgrading that, and I'm always happy to talk about that if you've got questions later on. So in terms of what we're doing here, we have this is going to be a quick and simple, or a basic, I should say, console application. And so we're going to, I'll run this in a moment. What we're going to do here is inside of our console application, the first thing we do is we create an actor system. So in this case, we're calling it the Hello World system. Every actor system has that name, remember. We had my system as part of the example in the slides. So this is called the Hello World system. And what we have here is we have one actor, which is a Hello World actor. Now note, we don't say new actor. We give it, we say system.actorOf, and that is what will create an actor. And we pass in some props, which in this case is just pretty much the plain vanilla create a Hello World actor, and give it a name of Hello World actor. So we will have within the Akka system /user/Hello World actor in terms of our hierarchy that we create. I'll go into what this Hello World actor does in a second as well. We'll open that up. And then in an infinite loop, we ask someone to enter their name. We read the text that comes in for them entering their name, and then we tell the Hello World actor a message. There are two things that you can do in an actor system. You can tell an actor a message, which means that you don't care about the response, and this is the expected, typical way to go. You want to tell an actor a message, or you can ask an actor a message, which means that you anticipate a response message from that actor. Now that's where we get into some trouble with distributed systems, right? We need how long should we guarantee that message takes to receive it? Should it be received the response within 1 second? What happens if the response is not there? And so typically what we do is we tell an actor a message, which is more of a fire and forget. I'm going to put this message in a mailbox queue. Akka will help you and make sure that that message does reach its intended recipient. But beyond that, then you're not waiting for a response. If you need a response, maybe it'll send a message back to your mailbox, and then you'll process it in the order in which it's received. So in this case, if someone types in the phrase end, we will tell the Hello World actor a new finished message. And otherwise, we will, if someone doesn't say end, we'll send the Hello World actor send a new Hello World message, and we'll pass in the name that was provided. So let's look at the two things first. We're going to look at what the finished message and the Hello World message look like, and then we're going to look at the structure of the Hello World actor itself. So here's some our messages here. So a Hello World message is an immutable object, takes in a string called name, and then sets a public property called name, and then that property is read-only. So beyond the time that object is created, typically, I mean, you're not really messing with the structure of that object. It will have one property called name, and in order to create a Hello World message, you have to pass in the name. So the name has to be there, sort of a contract that your other actor can expect. In the case of the finished message, it's just an empty class. We don't really have any additional information to provide. What we need to process there is here. It's the idea of we're telling it that it's finished. There's no additional information or context, so we don't have any other additional properties in our class. So let's look at what this Hello World actor actually does. So a couple things are going on here. First, you're going to notice that the Hello World actor inherits from something from the framework called receive actor, right? Next, we see that it has an iActor_ref to something called a console writer. When we create a new Hello World actor, it gives us a reference to the console writer actor by calling context.actorOf and creating a new console writer actor. What this does is now this Hello World actor, it creates a child actor of type console writer actor. So this would be at /user/hello world/ whatever random name Akka.NET gives it, since we don't give it a name here ourselves. And we have, as a result of that context.actorOf, it gives us an iActor_ref, which we can refer to here. Next up, we see these receive commands. This is how the actor is going to behave when processing a message. So when it receives a Hello World message, it passes in, we know that we have a strongly typed Hello World message here, and it's going to tell the console writer a new write something message. In this case, it's a message. I'll just look at that real quick. It's a message that passes in whatever the thing to write is. And so it's going to write hello, message.name, that name property from our Hello World message variable. And it's going to say that it was sent from itself. Now, this is to tell the actor that's receiving it where it's coming from in case that actor should choose to write back. But we don't have to necessarily respond or include that. And so lastly, here we have the finished message, in which case it will just write, I guess we're done here. So let's go ahead and we're going to run this example and just see how this plays out. Okay. And if this is a little small, I apologize. I'll try to narrate as well, see if we can. I realized I hadn't increased the text size, but hopefully we can see it says enter your name. So in this case, I'll enter Shawn, and we can see here that after entering that, the hello world system /user /hello world actor is sending a message called hello Shawn. So the hello world actor sent that to the console writer. The console writer said, write out whoever sent that message and then write the message itself. And so like same thing here, right? I can do various names here, and we're getting that response back from that console writer actor that's been told a message. Similarly, I'll go ahead and hit end, and let's see what happens here. So you'll see what happens in this case. Actually, the program sort of finishes, but we're still waiting for the actor system to terminate. And so we see the actor message asynchronously prints out, I guess we're done here, even after that console program is terminated. Just by nature, it's operating asynchronously in terms of how it writes out that text. So I'm going to go ahead and hit enter there, and we'll stop that project. So that's sort of not a basic, but a initial hello world kind of application there, where we have an actor with a console writer. The actor takes input, it sends a message to that console writer actor. You see the output on your screen. So one of the other pieces that we talk about here is the idea of becoming and unbecoming. So I opened my program here, my demo under become, unbecome. So what we're going to talk about here is how Akka.NET can change its behavior based on items that are coming in. And so what we have here is I have an actor system again in my console app. I'm calling become, unbecome demo. I have the idea of a variable writer, which is an actor system.actor of a variable console writer actor. We'll look at what that does in a second as well. Again, in an infinite loop, I say some things. If, when console.readline occurs, it's then going to tell the variable writer a new write something message. And so that variable writer is going to do something when it receives that write something message, which again is just the string of text. There's no other properties there on that class. So let's look at what the variable console writer actor does. That inherits from implies an interface and it inherits from receive actor still. But you'll note this I with unbounded stash that's happening here. So what this actor is doing is, upon being created, it takes its initial state, which is we're calling a normal writer. In the normal writer state, whenever it receives a write something message, if the message is be quiet, it says zipping my lips, and it becomes what we're calling a quiet writer. Otherwise, it says the message that you sent in. And in this case, it's not using a console writer actor, it's just calling console write line directly. So then when it becomes a quiet writer, what happens is when it receives a write something message, unless the message is be loud, it stashes the message. It stashes it for future retrieval. And that's a functionality that's built into the actor based on that, and you're able to surface that using that I with unbounded stash interface. And so if the message is be loud, it'll say letting it all out. It will unstash all of those messages that it's received, putting them back into the actor's mailbox in the order in which they were stashed. And then it becomes a normal writer so that upon processing the next message in the mailbox, aka the first message that was unstashed just there, it will then process that normally. So it's changing its state based on the messages that it receives. And so I'm going to go ahead and run this just to show what we mean here. So we'll say some things. We'll say, hello. All right, we see the message come back. Hello, world, blah, blah, blah. I'll say be quiet. Zipping my lips. Now I can say hello, world, RV.NUG, what's up? Right, and that's all being stashed. It's not writing anything out. That's being stashed in Akka's stash there. I'll go ahead and say be loud. It'll say letting it all out, and then it'll pull those messages back into the actor's mailbox, process them in the order in which they were received, and then we will see the output to the console in this case. So that is an example of an actor sort of changing its state based on what's coming in to that actor framework, or to that specific actor rather. So before we go any further there, I've got to jump over and do one more command here in my VM. So do we have any other questions so far?
Oh boy, there's a lot there.
And that's okay. I know it's a lot to drop. It's a lot to drop initially. So definitely feel free to hit me with a few questions.
Yeah, so if you stash things, is there like a background mechanism where it can retry stuff, or is that something you have to explicitly write out?
So actually, it's a great segue because we're going to talk about supervision and retrying items. So stashing, you can choose how and where you want to use the stash mechanism. And I should mention this is all happening in memory. Akka has other libraries like Akka persistence. If you needed to make sure that those messages were durable, or that if the power cord got yanked, you'd still have them all to replay. So it's got mechanisms for that sort of a thing as well. In this case, that stash sort of exists in memory, and the Akka framework is handling that for you behind the scenes. So you could, if you hit a message and you had an error, for example, when you had your supervision strategy, you could choose to stash that message that you just got and retry it in a second. So you can sort of take those strategies, and that stash is a very useful mechanism for storing those messages for retry or for sending them somewhere else, or really whatever purpose you need to stash them away for. And so we'll show an example of that with our supervisor strategy in one moment. All right, my VM is now installing .NET 5, so it's going to be set up here for use, and we'll go on with our demo for now. So let's talk about supervision. There's a great segue there. Okay, so this is a little, again, these are contrived examples, so I appreciate you bearing with me, right? We're talking about console apps, but this is mostly so we can try to focus on the theory of actor systems. So in this case, we're going to talk about supervision and what to do when things go wrong. So the first thing we're going to do in our main console application here, we're going to create an actor system again, called supervision system in this case. We're going to create what we're calling a parent actor. We literally have a class called, or an actor called parent actor, of type parent actor. And that's going to be a top level actor in our actor system, and it's going to have the name parent actor. So one thing I note again here that we're not passing it around as a variable, we're creating a reference at a location. So we're creating here the system.actor of, and we're creating a console writer actor again, and we're calling it console writer. So now we have two actors at the top level of the system. We've got supervision system / parent actor, supervision system / console writer. So those are two actors that are going to exist in our system. What we're going to do is, for a number range from 1 to 100, we're going to tell the parent actor to process a number, and we're going to pass in the number that we want it to process. And then we're going to wait for the actor system itself to terminate. So let's look at this parent actor and what it does when it receives that process a number function. Parent actor, again, inherits from receive actor from the Akka.NET framework. It has an iActor ref to something that we're calling volatile children. So these are children, and you're getting the sense that maybe these child actors aren't going to be super sturdy. So when we create a parent actor, it's going to automatically create a child actor. In this case, we had children because there may have been more than one, but we're actually really only creating one here. So we have a parent actor. It's going to create a volatile child actor. And then we get a reference to all of the children. So if we wanted to create 5 child actors here, we could. And then what happens is when the parent actor receives a message to process a number, all it does is pass that message directly along to its volatile child actor. So the parent receives a process a number message, and the child actor will also be able to receive a process a number message. We'll look at that in a second. The parent actor here also has something here called a supervisor strategy. So we can see return new 1-for-1 strategy, local only decider, directive.stop. This is saying that at the parent actor level, should any of its children have an error, what's going to happen is it's going to stop that child actor that had an error. So first what I'm going to do is I'm going to comment this out. Right, we'll pretend we don't have a supervision strategy at all. Let's look at that child actor briefly and see what it does. The child actor, again, has the idea of a stash. We're not using it currently, but it has it contains state for the number of messages it's processed. And when a message is received, it says, if the number of messages I processed is 6, I'm going to throw an exception. I already processed 6 numbers. I'm too tired to process whatever number comes in. Right? And so again, pretty contrived. Otherwise, if it doesn't equal 6, it's going to increase that state, which we're just incrementing an integer. We're not doing anything with thread safety or anything like that, right? It's just processing a message and changing its internal state based on that one message. And otherwise, right, it'll say it's processing that number. It'll write that out to the console. So let's look at how this plays out in the execution of our demo here. So I'm going to run this demo. We'll see an error pop up, presumably. All right. So we see, an exception was thrown and it's unhandled at this point. We haven't set up any handling for it whatsoever. So here we can see, let me go ahead and continue. We can see processing number 1, 2, 3, 4, 5, 6, and we just lost number 7. There's an error. I chose to keep going. It's gone. I don't know what happened, right? At this point, the program could blow up, but I'm in debug mode, so I can keep going, right? So the actor system has sort of caught it for me, but I haven't handled anything yet. So I can kind of keep going, but I'm going to keep getting these errors, and I'm going to keep missing that process. Something happened there. I'm too tired to process number 28, on and on and on until we get to number 100, but we'd be missing that entirely. All right, so I'm going to go ahead and stop that process. So that doesn't seem super reliable. We can't change our child actor maybe, but we can do some other things here. So let's look at our supervisor strategy here in our parent actor. First, let's look at the strategy there for stopping our child actor. So now if that child actor throws an exception, what's going to happen is you'll see an exception. Okay, we got the exception, right? It's happened. Let's go ahead and hit continue. And then we see a bunch of stuff in our console. So let's take a look at what that is. 1, 2, 3, 4, 5, 6. I already processed number 6, too tired to process number 7. And then what happens is we can actually see that it didn't deliver the remaining messages to that actor. It was stopped. So that actor couldn't receive any messages. We only had one actor there, and it was stopped. And so Akka is telling us now, this is the framework telling us, we tried to send this message, but instead it went to dead letters. Right? We passed in that message. We couldn't do anything with it. It couldn't be delivered. So it went to dead letters, which is a system level place where we can still do some recovery if we should choose to. But all of those other messages went undelivered. And so our application just kind of does nothing at that point. So what if we were to restart instead? So let's go ahead and say in our parent actor, instead of directive.stop, let's see what other options we have. I could do directive.escalate, directive restart, resume, stop. So let's look at if we wanted to restart the actor, what would happen. So we'll still see our exception as you might expect. We'll go ahead and hit continue a few times. Let's look at what it's got here. So one of the things, I was accidentally holding the console here. Let's see if I can. One moment here. Let's try that one more time. So we're receiving our item there. We're hitting those numbers. You can see process 6 numbers, too tired to process. So we've now restarted the actor. So we're sort of back to where we were because the default is restart. So we're doing the default behavior right now. So it passed 6, but it restarted the actor and it continued processing messages, but it missed that number 7, right? And similarly missed that number 14. So what if we were to do something a little different? We can restart the actor here, or we can hook into some of those lifecycle messages. So that volatile child actor, remember we're using unbounded stash on that. So let's look at some of this code here. What if before we restarted, we stashed the message, and then after we restarted, we unstashed all of those messages, right? So now we have the option to sort of do a really cheap, quick, and dirty retry on this. And so our parent actor, right, we haven't changed it at all. We'll leave the directive as restart here, which is again the default behavior. And let's go ahead and run this and see what it does. All right, so we still get our errors, right? We still get our 7 couldn't be processed, 13 couldn't be processed, 19. Those numbers are a little different. So what's going on here? We can see here, we actually did process number 7. Right, so we restarted it 1, 2, 3, 4, 5, 6, 7. We processed it. And we're still doing them in order, so we actually haven't even lost our sequence of messages there because that actor is being restarted. Now, if we had multiple actors operating, of course, this would be asynchronous. We might not process them in order. That's kind of just a side effect of the fact that we had one actor that was restarting. But the key there is that we didn't lose those messages. Right, we didn't miss them. We didn't have some sort of weird state that the system got into because it couldn't handle what it was doing. Oops, I meant to keep that screen shared. Let's keep that going. Hopefully, you can see this again. Okay. All right, so that's the idea of supervision there. Is with those supervision strategies, we can recover in those cases. And so the last thing I want to show you is the idea of routing in Akka.NET. And this is what I started to talk about in terms of configuration and being able to deploy actors in different ways. So let's first introduce this example about routing. So in my console application, I've got some configuration, which we'll talk about in a second. I put it in here so that we print out at startup, and it just was easier at the time. But this could be in a configuration file. It doesn't have to live in your C# as a string. In fact, it normally wouldn't. But so let's set that aside for now. I have an actor system called the elastic system here that takes in that configuration, which in this case is a variable, but otherwise can be read from a file, etc. I have a demo actor, which is a top-level actor under that system. So elastic system / demo actor is the name. I tell the demo actor to start a demo, or I send it a new start demo message, which has no properties or data associated with it. So let's look at that demo actor and see what it does when we start the demo. So the demo actor has a child called random number after random time worker, which hopefully gives you.
Are you showing as
I was intending to show that screen, the code. So let me see. Let me reshare it here. That would be the appropriate screen. Instead, there we go. Thank you. That's better. So let's take a step back. I was worried that I shared the wrong screen last time. So I've got some configuration here, right? That's in a C# variable that we're going to ignore for right now. We create an elastic system that takes in that configuration, that Hokan config. We've got a demo actor here. That's a top level actor there. We tell the demo actor a new start demo message. So let's look at that demo actor. The demo actor, again, inherits from receive actor, like all actors, or like 99% of actors do. And it has a child actor. When we create a demo actor, it's going to create a child actor of type random number after random time worker, which would give you some insight as to what this worker might do. Don't mind the commented code. We'll get to that in a second. And then what we do is we create that random number actor, and then we create a console writer actor as well, so we can write some stuff out. And that is a child actor of the demo actor, because it's context.actor of, so it lives within the hierarchy of that demo actor. So we say the demo actor started, and then we say we say where it's created and where it lives, just so we can print that out for debug. Whenever it receives a start demo message, it's going to say starting demo, and then it has going to use this great feature of Akka.NET called the scheduler. It's going to schedule a message to go out repeatedly. It's going to start it immediately. There's not going to delay the start, and then every second it's going to tell the random number actor to generate a new random number or generate a random number message. It's going to send that message to the random number actor. The random number actor, so we can. Oh, sorry, let me look at the random number after random time worker actor. What that's going to do, it's got its own console writer child as well. And then it's, write something message. I've been told to generate a number. And then it will create a random number from 1 to 10. It will pull a thread.sleep, right? So it's actually going to sleep on that thread, right? So we're not doing anything kind of fancy. We're not awaiting that. It's straight up calling thread.sleep. Like it's going to put that thread to sleep that it's running on for however many seconds that is. And then then we'll generate a random number between 1 and whatever that number is. Then it will write that out to the console via that console writer actor. So again, just to walk you through what's happening here, right? We're going to have the demo actor that is going to, when we send that start demo message, it's going to start every second telling that random number after random time worker to generate a number. So let's look at the what we've got going on here first in that demo actor, the commented code. First up, we're just going to create one actor, right? So we're going to go ahead and create a single actor. Let's look at what this demo looks like when we just have the one actor. Okay, so it prints out the configuration. We see that there's a demo actor. There's a lives at /workers. We see down here the random number actor is given the name of /workers. So it waited 7 seconds for the first one. It waited 2 seconds for another one. It waited 6 seconds after that request, 1 second. So it's chugging along. It's doing its thing. But those messages are being sent every second. So it's still piling up in its mailbox, but it's processing one message at a time. And so they're sort of queuing up in this actor's mailbox. So that doesn't seem very efficient at all. So let's, instead of creating that single actor, let's utilize the idea of a router. So let's look at, instead of creating a random number after random time worker as the child, let's create a random number after random time worker with a router. This is an extension in Akka.NET that allows you to just add a router to your actors and put multiple actors underneath that router. So sort of creating its own little hierarchy. So in this case, we're going to create a new round robin pool. There are different kinds of pools and groups that you can create in Akka.NET. So round robin just means it's going to go child by child and send the message to that child. So the router, a message will come into the router, it will send it to the child in a round robin fashion. So let's look at what that looks like when we run it. Now we've only got one instance here, right? So we're still, probably not going to see much more throughput, but we'll see some of the output here. We can see now workers /$A. Akka has created a round robin pool with only one actor in it now, but it's sort of given that actor the the system name of $A because we haven't given it any specific name. So it's got $A behind that router, but still just one actor. So what if we wanted 5 actors because we wanted a little more throughput? Let's go ahead and, again, this is overwriting what I'm doing before, but it'd be the equivalent of commenting that out there. So now let's say 5 actors. How's that going to work? It's going to go ahead and start remoting. So I've been told to generate a number. Right, so we see now that A, B, C, D, E. That round robin was still getting picked up, right? So every second, a message is being sent to one of those items, and now we can see we're getting a lot more throughput. All those 5 actors are doing work. The messages are queuing up still every second, but it's going and being spread across those 5 different actors' mailboxes, all by adding sort of one clause to our code, which is pretty neat from where I'm standing. But what's what I like even better though is the idea of saying, right, what if I wanted 10 actors? Am I going to come into my code and change that 5 to a 10 as part of a design configuration? This may be an operations concern, right? This may be that they need more throughput. Maybe they don't really need me around as a developer. Maybe I'm not even there anymore. Do we really want to do a new release just to try to peg that? We probably don't. So instead, let's pick up that router from configuration. And now let's go ahead and look at that configuration that I had breezed past before. So what we've got here is it'll take some routing from a configuration. I've got this commented here currently, right? So what I can do though is I can say, okay, for the actor that is deployed at the path demo actor /workers, don't actually deploy one actor, deploy a router in a round robin pool with 25 actors. Now comment that out. We'll leave the remote blank for now. So let's go ahead and see how that works, right? So this is going to pick up that from configuration. We should see 25 child actors created as a result of this. So let's see, we've got A, B, C, D, E. We should go well beyond that. We got F there, G. And so now we're back to, I haven't made any changes to my code technically, right? I just said, hey, take this from configuration. And since I've specified some configuration for that path, with that small change to a config file, I'm able to now create create some real efficiency there and scale out that by just putting a router in front of it. And that's all being able to be done through configuration. And that's great. And this is nice. It's all living in the same process. And I've got my code here, and that's great. But what if we wanted to do it in 2 different processes? So what I've got here is the idea. I've got an app here called Blank Slate, just to be clear. So it's got configuration as well, but what the configuration does here is it just says, okay, I'm going to utilize something called Akka Remote. I've got some network settings that say, hey, I'm going to run it localhost here. I'm going to run on port 9001. It's going to create an active system called Blank Slate, and it's going to say, sitting here doing my thing. So what you'll notice is that I'm not creating any top-level actors here. I'm not doing anything for this, right? So if I was to run that, on its own right now, this is all we would see. Starting remoting, it's remoted and it's listening. It's not doing anything, has no actors deployed to it at all, right? So it's just kind of a blank slate project. So what then if I was to take this demo actors program and uncomment this last line here that says remote equals blank slate at localhost on port 9001. Let's go ahead and let's run a debug instance of that blank slate app. All right, so sitting there doing my thing, and let's go ahead and run that routing app with that configuration change there. We spit out its configuration, right? And you see starting demo, right? And it's blank, but it's blank because it has deployed those actors to the other process that is running. So that's the actor system that had no other knowledge of the actors except for that shared DLL file that has the the composition of the actors, and now it's doing the work in a completely separate process. Which is kind of neat, but this is still .NET on Windows and yada yada yada. So let's go ahead and let's go back to my instance from earlier. Let's go and we'll share my other screen again. All right, so I've got WSL open here, and I'm remoted into that VM in Azure, the Akka intro VM. Let's just go back to my code here. Let's see, I think I got it in code. Let's just do a .NET restore. While it's doing that, I'm going to double check that I've got here. I'm going to have to modify the settings. That's fair. Okay. Right. So before I build and run it, I'll do that. Okay. And double check that public IP that I've got somewhere around here. All right. So it's restoring that. Now this is a pretty inexpensive VM, so it may take a second. So I appreciate you bearing with me here. So we're going to restore, and I just want to be key that we're pulling from the same repo that I just spun this up from, same exact code. And so I pulled that, and we're going to build this project now. Wasn't quite expecting it to take that long to restore. I'm sure the network connectivity / very low budget Ubuntu VM is going to be a little smaller, but that's all right. Once that is done, we will go ahead and, all right, so we're going to go into blank slate. I think I need to modify it. I'm going to go into modify that program there. And I'm going to, this is the first time I'm doing this, I've got some directions for myself. Set the public host name to the private, the public IP address. Set the private host name to the private IP address. Okay. So let's go ahead, and the public host name is going to be the public IP address here. Should be able to paste in a second. Okay. And the private host name is going to be, I got to go back to here. So just kind of wiring this up so they can actually get to things on the network. I'm going to go ahead real quick and I'm going to save it. And I'm going to run ifconfig real quick just to 10.0.2.4. Okay, so go back to that. And I'm going to set that correctly. 10.0.2.4. All right, let's go ahead and save that. All right, now I'm going to go ahead and do my blank slate. I'll do .NET build and .NET run. So again, this is building my application on an Ubuntu VM on Azure. And I'm going to go ahead and I've pasted, I'll go back to my screen here. I'll pull it over side by side in a moment. Okay, so we see there it's saying sitting here doing my thing. I've modified my configuration to refer to that public IP address there, and that IP, I'm going to go ahead and run my program.cs. So see starting remoting, it's starting the demo, And we can see here, there it is in an Azure VM, in Ubuntu, not on Windows, taking messages and actually instantiating entire actors and an entire actor system and hierarchy in a remote process on a remote machine. And all I had to do was change the configuration there. And you'll note we're also getting 25 different actors there from our configuration before. So with a simple configuration change at that point, because we're using this actor model, we were able to deploy those actors to an entirely remote location. And so that's some of the power of the actor model here. And so what I want to really get into, just to end the process here, is the idea that remoting, and I showed a demo of remoting itself, but there are really great libraries and features of Akka that are built on top of this remoting feature, such as persistence, where you can store your messages in a SQL Server DB or a Cassandra DB or anywhere that you might need them to be stored prior to your picking them up and processing them by an actor. There's also Akka clustering, where you can set up groups of these sort of servers and nodes, and it uses Akka remoting behind the scenes to do really steadfast, sturdy clustering, so that you can have groups of nodes with different purposes doing lots of processing of messages at once. And Akka also has the idea of Akka.streams for doing kind of streaming and streaming versions of actors if you need to have streams of information that do backoffs or things like that. There's a library or features built on top of the Akka platform to enable you to do those things. And so if you're interested in more, and I hope after this talk you're interested at least in exploring, because it was super fun for me to get into this. The website is at getakka.net. Don't forget those, Pettbridge.com has that great boot camp. And Akka.net, well, the last thing I'll say, phenomenal project to get involved in as an open source contributor. If you're ever looking for a place to get involved or help out, or you want to really dig into this technology, that crew is really welcoming there. There's a lot of stuff you can do, and they're always looking for help, like many open source projects. So if you want to make an impact, definitely look into this or another open source project, because I guarantee you there will be a place where you can make a contribution. And other than that, I'll say thanks for now, and we can open it up for the one last round here of questions, and we'll see if you can wear me out, and then we'll bid you good evening. All right, so with that, I'll go ahead and stop the screen share, and we can jump over to some more questions that you might have.
No question. I just wanted to thank you for your time. It was very informative and worthwhile for me. Thank you.
Oh, thanks. I'm glad to hear that. This was I remember seeing a talk on Akka.net some years back at .NET Fringe, and I remember saying, "Oh, this is going to be fun to play around with." And since then, getting to do a few implementations in production with the system, I can say there's a ton of benefits. So it's if you do nothing else with it, I hope you play around with it a little bit more. But I'm glad that it was at least worth your time. That's my baseline for presentation. So I appreciate that.
Oh yeah, that's fantastic. Thank you, Shawn. I do have some questions. So I'm trying to think about that external process. What if the external process was down? Can you have multiple external processes, and then it kind of picks which process it can deliver to? And what happens with it if it can't talk to anyone? Does it retry, or?
Right. That's a great question. So say for example that process was down, what would happen is it would be similar to the example I gave where I stopped the child actor in the supervisor scenario. So things would start going to dead letters. It would say, hey, I can't reach anybody. Now, if I was building clustering from the ground up, maybe I would have that in that config, several remote actors deployed. And I could do that. I could say, hey, have actor A deployed in this process, have actor B deployed in this process, have a round robin router in front of that. But at that point, if I'm looking at doing something like that, I'm probably going to jump to using Akka.net's clustering, which has really great abstractions over those sort of concepts. So if you know you're going to be doing something with multi-process to start out with, I would probably start there. They've got some fantastic theory and tutorials on how to set up and think about clustering and roles and how to deploy those there. And at that point, that configuration would become a little less necessary, as you'd be relying on sort of clustering in general to accomplish that.
That sounds like incredible features. Are these features all included in a open source version, or is there a professional version?
So one of the beautiful things about Akka.net, all of this stuff that I've shown, plus clustering, persistence, all of that stuff is free and open source. Where Pettbridge is adding a product offering is around some great enterprise grade monitoring and logging for actors. You could build what they do all yourself, but for those who are running Akka.net in an enterprise environment where that traceability and visibility is really key, you probably don't want to write that all yourself, and they have great value add product that they have on top of that. For you to do monitoring and management of Akka clusters and things along those lines. So you could do that stuff yourself. It's a little tricky. There are libraries out there to do it, but that's sort of where their product offering is. And I found, at least in small scale production implementations, if you're doing logging on your own and you've got some logging set up, in my case, we did a production implementation that used Serolog and went to a Seek instance, so we could kind of search and see what was going on reasonably well. We had a small volume of traffic, and so that was really kind of manageable for us to do. If I was doing a larger implementation, I think it's a no-brainer in terms of the pricing and commercial offering. And they've taken great care, and Aaron's actually written about this before, I think, to really only do commercial offerings where there's like a real value add for business, all of the core functionality of the library, I believe the goal is to always keep that open source so that anybody can use it and make use of it. And it's really only to be those kind of value add items that would be added for commercially. So I would say, I can't say I'm 100% certain on that, but I'm like 95% certain that that's the strategy.
This is really amazing. I write a lot of things that implement similar things to this. I do message processing and whatnot. I usually, spin up a bunch of the threads, and they have to communicate with each other, and make sure that they're not stepping on each other, and or trying to avoid deadlocks is a
Sure.
field. And
Yeah.
doing this for a long time. It started with C++, and wow, that was a nightmare too. C# definitely, with all of the threading and the task library and whatnot, makes huge improvements on reliability of doing that sort of thing. But still, there's a lot of manual things. I am definitely looking forward to using this,
Great.
future project here.
Yeah, it does take some adjustment.
Talking like, what all do I need to rewrite now?
Yeah, and it does take some adjustment, especially if you're working with a team. One of the things we found out when we started exploring it is, it is a different paradigm, right? So it's a different way of thinking about how you're going to structure objects, how you're going to push work. If you have large chunks of work, chances are you want to keep pushing riskier pieces further down the hierarchy. And so you don't get it right the first try necessarily. But if you're thinking about it in terms of, okay, I've got a person that's going to distribute work amongst these other people that are going to do some smaller bits of stuff, and you get used to the idea of telling an actor a message and not being able to expect a reply from that statement, and you have to just kind of process it when it comes back. If you start to model your systems with those constraints in mind, I do find it makes thinking about async just so much simpler. And because of the excellent thread management that it's doing for you, you get so many benefits, and you lose a lot of that cognitive overhead of building these kind of your distributed reactive applications.
Yeah, it seems like it would take just a great deal of experience before you could even build a system. I feel like I would build a system wrong like 5 different times in Akka.NET before I like really understood, because it seems like it's just a completely different paradigm, like switching from OO to functional. You're gonna write it wrong in functional until you really kind of grok what functional is and how you solve problems differently with it.
In a sense, yes. I will say it's definitely, I think it's an easier bridge than functional for most object-oriented developers or people who've been working with C# by default for a long time. But I do think that you're right in that you have to allow for that learning curve and for trying things and maybe getting it wrong a few ways. But I think that just as a counterpoint, though, I was able to take a team, and granted, a team of great developers, but for a client project, right, we said, oh, we're doing a lot of stuff. They're processing it in this request response model. In this case, in my client's case at that time, they had a lot of long running HTTP requests that would do a lot of processing, maybe fail, could take on the order of an hour sometimes, right? And then would return a response message. That is not suited for HTTP. That is, you're asking for pain. And so they also wanted that recoverability. So it's kind of like, oh, light bulbs started going off. And so we said, okay, team, we're trying to go this route. And what we did is, right, we did almost the strangler pattern with it, right? What is some of this functionality? We took bits of it piece by piece and moved it into that actor-based system, right? And then we had, so we had that long-running request of talking to the actor-based system and getting responses. We moved more and more of that functionality into the actor-based system, and then eventually we were all in on actor land. And so I think that you can still kind of get those benefits, and because the system's pretty easy to refactor in the actor way, if you have a whole team on the same page about how they're thinking about it, you invest the time in the boot camp, you talk about some of the theory, you kind of have an open space for people to explore how you would model a system like this, then I think you can get a lot of good results. This is another place where actually, and I promise I'm not endorsed by Pettbridge in any way, but this is another place where I think they have some great material. Is I mentioned they do that paid offering for monitoring. They also do paid training sessions, and the 2 training sessions that I highly recommend because I took them are the intro to the actor model, and then they have an entire one that's just on modeling applications with the actor model and thinking in this paradigm. So they go through clustering and how to think about that, and how to break down a problem, and how to establish all of those models, how to think about your domain and those constraints. And so I think that ends up being a really big value. If I can recall correctly, unless they've upped the price, is a pretty good value for money and time. So there's other things you can do there to help kind of get your team state of the art to include the idea of the actor paradigm. And last I checked, the system that we did build is still running happily in production. So. Okay.
Cool.
How about compatibility? What frameworks does this support? How long has it been around? Is this rather new, or has it been around forever?
It's been around for quite a while. I think it's been in production back since I probably saw when was the first .NET Fringe that I went to? 2016 was when I first learned about it from Aaron, who had, I don't know if Pettbridge was fully off the ground at that point, but certainly Akka was off the ground there, and Aaron was there telling the story about sort of how Akka.NET came to be and showing some demos. So it's been around for a little bit now, for sure. It's definitely been battle tested. It's getting used in all sorts of places, in finance and I think automotive and some other ones. They've got some great use cases and case studies on their website about it. So it's definitely been around in terms of that.
Nice. I noticed you said I think .NET 5. So
Oh yeah, so
the latest.
they're supporting the latest. Yep, it'll work on .NET 5, .NET Core. It works on .NET 4.7 and 4.8. It's what all my demos were originally in. I don't know about the support. I want to say it works on .NET 4.6, but I'd have to check myself on that. But typically, I think it's pretty versatile in terms of where you can run it. You're going to get a lot of throughput and performance improvements if you are going to that .NET Core, but it'll run on the legacy framework, definitely 4.7, 4.8, unless they've recently dropped support for something. But these demos, until I recently redid everything in .NET Core, these demos were all on the full framework 4.7.
Oh, good to know. Yeah, I know we have still good bit of property running in the .NET full framework. Migrating now. I think many companies are migrating to .NET Core, but still good bit out there. And Windows ships with 4.8, so
Absolutely, and I think they know enough to not. They knew enough to not upset that ecosystem, right? They know that .NET spans from early adopters to laggards in terms of the framework, and so I think it's got some deep compatibility there because it really is about moving paradigms more than it is about moving frameworks. And so you'll get some additional benefits, I think, if you're on some of the later bits. But they've done a good job of making it compatible.
Excellent.
Cool. All right.
Let's see. I do have one more important question.
Sure.
How are you getting your this is slightly off subject here, but how are you getting your gray type inference and parameter names in Visual Studio?
Oh, let me see. I think let me pop back over to that. I don't remember
really cool.
offhand
I
which tool
really
it
like
was.
that.
Let's see here. I want to say, let me see. You're talking about this right here, right?
Yeah.
I want to say that's ReSharper doing that. I could be wrong. I think that's ReSharper. It could also be Ozcode doing that, but I think I'm currently using ReSharper, Ozcode, and Ncrunch. So I want to say it's ReSharper, but it's either ReSharper or Ozcode. Ozcode is doing both fantastic extensions that I love very much. Ozcode is doing does a lot of great stuff at debug time when you're looking at stuff and you need to step through values and do some kind of what ifs. Ozcode is phenomenal about that, but I'm not certain which one it is. Given that I see this menu here, I'm tempted to say it's parameter name hints from ReSharper.
I thought that was the fancy version of Visual Studio.
Well, now let's see. Let's go to configure. Configure pulls up the ReSharper options. So it looks like at this point that is coming from ReSharper.
Gotcha. And that's the paid version of ReSharper, right?
Yes, I don't know if there is an unpaid version of ReSharper.
I didn't know.
Yeah, I'm not sure. But ReSharper is a commercial product that I've loved for a long time. That's one of those things where when it comes to developer productivity, I always look at like time for money value. And when I looked at the productivity gains I got from ReSharper and from ReSharper and Ozcode, and there's another one called Ncrunch that I use that continuously runs your automated tests in the background whenever you type a key. The value for those tools so far outweighed the price of them that I've been like a happy subscriber to all three for a while now. I think I'm lucky enough that if I recall correctly, I think I get benefits from ReSharper from my MVP subscription, but I don't even know that I'm using them right now. I think I'm just still a paid customer because it's a fantastic tool. So
that's really good to know. I've seen ReSharper many times, and this I don't know, this might have to put me over the hump there and make me a customer there.
I will say that if you're on and now that Visual Studio is sort of, I imagine, going towards the idea of 64-bit technology, right? I imagine it's going to have to get there. The resources that Visual Studio has are going to be even better. The resources that ReSharper has as an out-of-proc application keep getting better and better. And so there used to be a huge performance impact to using ReSharper. These days, I barely notice it, especially if you're on a machine that has any kind of decent guts. You're not really going to notice that terrible slowdown that used to come, which, by the way, I still thought was worth it. But these days, on a modern development machine, I'm not noticing any setback at all there. Well worth the experience.
Right. I haven't heard about the Ozcode and Ncrunch. Can you type those in there, or?
Sure. Yeah. Like, in fact, let me. Sorry, I accidentally hit the wrong button. Let me go back to that. So the extensions there are Ncrunch for .NET and Ozcode there. So Ozcode is fantastic for like breakpoint debugging and doing kind of various step-through functionality. There's actually, I think, a lot of functionality there that I still haven't even tapped into, that I'm still like learning about as if I hit a breakpoint in something and I'm having a problem, I'm like, oh, thanks, Ozcode, I didn't realize you could do that. And so it's great from that perspective. And Ncrunch, especially if I'm doing TDD, it'll show a little. I do whole talks on TDD with Ncrunch and some other things, and the amount of time it saves just being able to type a phrase and watch a test go from green to red as I type, rather than having to stop and compile and rerun my tests. Watching that happen with a small indicator off to the side as I'm typing, it does wonders for that like flow and productivity if you're doing any kind of like heavy automated testing session, or TDD as I often prefer. Which
Yes.
also, I should mention that
more.
Akka.NET has an automated test library with it as well. So I didn't show that here either, but you can do automated tests. There's a framework for testing your actors and your active systems as well.
And also making you aware of coverage, because you're constantly
Yes.
seeing your coverage information. So you're seeing whether lines are covered or not,
Absolutely.
whether you want it or not.
Yeah,
Which
so
was
that's
huge.
another tool well worth the money. Those are like my defaults. I'll put them on any machine, and I don't ever require an employer to pay for them. Like, I'm happy to supply whatever licensing I need, because they really make it worthwhile for me.
And if you're
Wow,
here's a cool tip I just learned. If you're in Visual Studio Code, there is a plugin called Fake Sharper, which uses the JetBrains command line version of ReSharper for free. You don't have to pay anything, and it'll give you all of the wonderful static analysis and some of the refactoring and some of the other benefits. Not
That's
quite as powerful as
fantastic.
ReSharper, but it's free and works on Linux and stuff. So that's kind of cool.
That is really cool. I have to check that out. And I know that someone's also working on porting the idea of like an nCrunch style product to VS Code as well. So I love it. I think it's such a great time to be a developer with so many people putting these great efforts into this ecosystem. And just when I think about the productivity gains that I have now out of the box versus 5 years ago, even, it's mind blowing to see how fast things are going. And it's really kind of a joy.
Mm-hmm.
Yeah, that's amazing. I thank you very much for the additional tips here at the end. Really good stuff. It sounds like we almost need a whole show just on developer tooling.
And I'll tell you what, as soon as you find whatever network wants to air that, you let me know, and I will sign up. Lee and I can co-host.
Tolga,
All
I
right.
actually have a ReSharper present. I have a whole ReSharper presentation. Probably Shawn does too. But
Yeah, no, I think I've heard about that presentation actually, Lee, and I have not seen it yet. So maybe you come back here sometime, and I'll get to watch you do it.
Awesome.
All right. Well, no, thank you for having me. I appreciate it. I think it's probably time I should go back to my family at this point. But no, I appreciate you all taking time out of your day to come out and hear about it. And certainly you've got my information, and I'm happy to talk dev stuff anytime. Love doing it.
It was really
Thank you very
fun,
much
Shawn.
again, Shawn. Really
Thanks,
enjoyed
everybody.
having you here.
Great. Thanks. Great to be here, and have a great night.
Thank you. All right, guys, check us out next month, June 3rd, microservices. The easy way is the wrong way. Come check out why. All right. See you guys next time.